Hello everyone, in this video we'll find the steady equation based on the coefficient beta and the coefficient kappa. Let's get started. In order to find the steady equation, the program gives us some information about the coefficients. Beta is equal to n times r over vt, and kappa is equals to a over v plus a function of p. In order to find the steady equation, let's go to suppose that v is a function of t and p. If it is true, we can calculate the total differential of v. The total differential of v is equal to the partial derivative of t times dt plus the partial derivative of v with respect to p times dp. Also, we need to remember that by definition beta is equal to 1 over v times the partial derivative of v with respect to t. If we solve this expression for the derivative, it will be gotten that the derivative of v is equal to v times beta. Same thing for kappa. Kappa is equal to minus 1 over v times the partial derivative of v with respect to p. If we solve for the derivative of v, we'll get that it's equal to minus v times kappa. This expression will be replaced in the total differential of the volume. If we do that, we'll get this expression over here. In this step, we can factorize the volume and we'll get this term. So now the volume rates multiplying the right side can pass to the other side, dividing like this. So let's go to replace the expression for beta and expression for kappa. That is information that we have in here. So let's go to replace them. Now we'll get this expression over here. dv over v is equal to all these terms. This expression here is beta and all this expression is kappa. So now we need to break up these brackets. So now we can pass this term that is subtracting this side to the other side with positive sign, and all the rest is exactly the same. Why did we pass this term to the other side? Well, that is because there are very similar terms. Both have the variable v in the denominator, so for that reason we have written the expression in this way. Now we can multiply all the equation by v and also by p in order to avoid work with fractions. If we multiply the expression by pv, we get this other expression. In here it's a little bit easier to work because we don't have fractions. Now let's continue solving this equation, passing this term to the other side and this other term to the other side, like this. So now we need, remembering this point, the definition of an exact differential equation. Remember, if we have a differential equation with this type of form, that differential equation is an exact differential equation provided that it achieves this condition. The partial derivative of n with respect to y must be equals to the partial derivative of n with respect to x. If it did that, we'll be able to solve the left side of this equation. So let's go calculate the partial derivatives. In the first case, we can calculate that according with this definition, the partial derivative of p with respect to p must be equals to the partial derivative of this expression with respect to v. If this gets achieved, our expression will be exact. So now, in the first part, we have the partial derivative of p with respect to p, but that is equals to 1. And in the other side, if we calculate this derivative, p is constant, so it can go out from the derivative and we'll get the partial derivative of v with respect to v. But this expression is equal to 1. So finally, we'll get that 1 is equal to p times the function of p. So now, solving for the function of p, we finally get that this function is equal to 1 over p. Simply, this expression, this p that is multiplying by the other side dividing, and it's in that way that we get this expression. So now we can replace this expression in the original differential equation, exactly like this. So we can simplify this term, p over p is equal to 1, and our equation becomes in this. Now we can observe, for example, the left side. These terms are pretty similar in a particular rule in differentiation that is very similar to the differentiation of a product. Think like that. If we notice, we've written this expression like this. If we solve this differentiation, we'll get this other expression. So for that reason, it's perfectly legal to write it in this way. And the right side, it's exactly the same. It doesn't have any change because we can't simplify it anymore. In this point, we're able to integrate both sides of the equation. In this term, we can eliminate the differential with the integral. In here, we can eliminate the differential and integral. N and R are constants. A is also a constant, so it can go outside of the integral. And we can integrate this term, p times dp. Solving all those integrations, we'll get that pv is equal to nr times the integral of dt is equal to t minus a, and the integral of p with respect to p is equals to p squared over 2 plus the integration constant. And in this way, we've found the state equation with beta and kappa give us in the problem. So that's it in today's video. Thank you very much for watching and see you next time. Take care.